What about this right here?
So what we're talking about today is a lot of the same stuff you did back with quadratics. Factoring and solving. What was the difference between factoring and solving? One was set equal to 0, the other wasn't. Which one was set equal to 0? Solving.
Yay!
Yay! So, in essence, you've done this. You just haven't done it with the higher degree polynomials. So what we're looking at today is just a whole bunch of examples of different ways of factoring and solving for zeros. Also, as we go through some of these things, as I'm solving for zeros, I'm going to start using the end behaviors again and start plotting via the end behavior, using end behavior, or dance moves, and all that kind of stuff. So, let's do this one. Well, first of all, we got to get the other one. I'm sorry you guys lost. I felt awful for Devin. I felt awful for Devin.
That was probably the saddest thing I've ever seen.
Yeah.
I was crying.
What happened?
Her other knee, I know.
That's literally all she worked for the whole year, just to get to play in that game.
I know.
What?
She got hurt before we started the warm-ups.
Thank you.
For a race.
Oh, well, you might as well hit it too. Should we put Devin's face on the ball?
Yeah.
Okay.
She can participate somehow.
Spell it right. See her thinking right now? Can you see it?
It's just I can't do O's. It's all like messed up.
And then these robotic guys, you guys are all over the place. What are you guys building? Like a lawnmower?
No, it was a drive sharing.
Oh, what? That stuff's pretty cool though. I know. Have you ever seen some of those robot things?
Yeah.
It's like Big Hero 6, but real.
So
If somebody made a Baymax, I'd love them forever.
You spell your name right? Are you sure? Was it Angle by mistake?
Small angle, like my seventh grade year, literally the first time.
Nice. All right, cool. So, how do I factor this one? When you're factoring stuff, a lot of it goes back into what's the first rule of factoring. And you're going to see this a lot with the upper degree polynomials. We're kind of doing the same stuff right now in pre-calc with 6 degrees and all that too as well. What is always going to be the first rule of factoring? What's the GCF here? 4x, good. So if I take out the 4x, I'm left with x minus 6. Are we okay with that?
yeah.
Now, if I set this equal to 0, I'm finding my zeros then. What are my two zeros? 0 and 6. So where does it cross the x-axis? 0 and 6. Using your tails dance, which way is this pointing? Up, up. Bless you. Where's your axis of symmetry for $1 billion? 3. What 3? Thank you. You get the bazillion dollars. X equals 3.
No, that's not fair.
Yeah, it is. So let's look at what's going to be new today. What's going to be new today is we're going to show you guys a couple of different ways to factor something that is a cubic. Yes, sir. Axis of symmetry is the halfway point into 0. So back when we dealt with quadratics, you had x squared minus 9. That's when we had what's called the difference of squares. So when you did that, you had x squared minus 9. You get x plus 3, and x minus 3. But yet, if we had it where it was x squared plus 16, could I factor that? No, I couldn't factor that because I'd get imaginary roots. Okay? But now when we get into a higher degree, there winds up being special patterns that happen. And we're going to have two of them, one for positive and one for negative. When you have are called a sum of cubes, and a difference of cubes. Turn off the phone, guys. Thank you. And what that means is that you're going to have to know some of your perfect cube roots. How to cube things off the top of your head. For example, what's 3 cubed? 7. What's 4 cubed?
64.
What's 5 cubed?
125.
Okay. So what happens is you get what's called in this problem, sum of cubes. And it follows the pattern. If the first term is a perfect cube and the second term is a perfect cube, so that's why I write as a cubed plus b cubed, and there's a plus sign between. The way that you factor it is you take the values of a plus b, square the first one, subtract, multiply them together, and add the square of the second. Whereas the difference of cubes, I want to put this up right away so you can see how similar they are. Really, the only thing you have to remember is that the first term for either of them will always be the same sign as it starts with. Yes, sir?
Why can't you just like put it in parentheses and write a root 3 outside of it? Like
Because that doesn't work. Same reason why you can't take the quantity x plus 10, or actually x squared minus 16 and take the square root. Same reason. Yes, ma'am? That's how you're able to get rid of your middle terms. Because if you think about it, when you start multiplying this stuff together, if you FOIL all of this out, you'd wind up with a squared b minus a b squared. The coefficients and the way that everything works, it winds up canceling themselves out. Okay. That's how we're able to get this. No. Oh, are you asking why is it a subtraction symbol in here? This is the pattern that happens. It's always, whatever this sign is always here. And then it's the opposite sign, and then the positive. This sign is the same here. Opposite sign, plus. The last term is always plus. And then the first little two-part one will always be the same, change, plus. Same change, plus. Same change, plus. If you just remember that, it works every time, whether it's sum or difference. Okay? This is a new one. It just takes a couple of problems to get accustomed to what it looks like. That's really all it is. Okay? So if I'm looking at this, my value of A is playing the role of X. The value of B is playing the role of 3. So if I write this out, then I get X plus 3, X squared minus 3X plus 9. That's how it's factored. A sum of cube, x cubed plus 27 factors out to be x plus 3 times the quantity x squared minus 3x plus 9. And like I said, if you FOILed all of that out, that middle term of the with an x value will go away. Which is how it winds up going away. So if I look back at the other one, I'm going to rewrite this one real quick. If I want to factor that one, what's the first rule Oh, it was sorry, it was 250.
Yeah.
I'm sorry. I was getting ahead of myself. What's your first rule of factoring? So we know that they have an x squared in common. But what else do they have in common? 2. They wind up with a 2 in common. So I can factor out a 2x squared and get 8x cubed minus 125. Okay. This now, when I'm factoring it, it's a difference of cubes. 8's a perfect cube. The cube root of 8 is 2. The cube root of 125 is? It's 5. So what you wind up with here, and as you get better at this, it might not be a bad idea to do this. This is 2x quantity cubed minus 5 cubed. That way you know what your a and b value is. Your a value is 2x. Your b value is 5. The pattern says, well, it's going to be a minus b times a squared. Well, the quantity 2x squared is what? 4x squared. Now, I started with a minus sign, which means my next sign will be plus sign. What's 5 times 2? So we get a 10x. And then it's going to be a plus 5 squared. And don't forget to bring that 2x squared along with it, because you've already factored it out. Yes, sir?
Where that 2x,
What's that?
where did 2x cubed come from?
What 2x cubed? 2x squared, you mean?
Oh, yeah, yeah.
GCF. First rule of factoring is GCF. No.
How did you get,
Sorry.
how did you get the 2x cubed over the 8x cubed?
I rewrote, what's the cube root of 8? What I did here is that this is my first term. Well, that can be rewritten as 2x quantity cubed. Because you cube 2 cubed the x, you get 8x cubed.
So then, how would you know 8?
Whatever the what I'm doing here is I'm letting a equal 8x. I'm using something called U substitution. I'm breaking this apart into using my exponent rules, because if I cube root 8, I get 2. So using 2x quantity cubed means I'd have to send that cube to both 2 and the x. 2 cubed is 8, x is x cubed, so that's why I get 8x cubed. Sir?
On the back where we were. So when you were to solve that out, would you distribute the GCF to just the first parentheses or to all of them and then you? Like,
If you had 2 times 3 times 4, are you going to multiply the 2 times the 3, then 2 times the 4?
no, okay.
Same thing. You just multiply. Okay. And that's what it looks like. It just takes a little while to get used to it. What do you got? The a value is 2x. So 2x quantity squared is 4x squared. A times b is 5 times 2x. That's where I get 10x. B squared is 5 squared, which is 25. Okay? That's why I'm telling you guys, when you see these things and you're doing these sums or the differences of cubes, rewrite them like that so you know what a and b is. Gentlemen, stop. What's that?
Why is there a cube?
Because, yeah, because what's 2 cubed?
But how come you don't write the winner at
Because you don't. The pattern is first term cubed, second term cubed. So it's just a plus b, a squared minus ab plus b squared. You're figuring out that if it's x cubed plus 27, that means x is A and B is 3. So it's x cubed plus 3 cubed. I'm just rewriting it, just like we would do with squares. Okay.
I think this would be easier to say that put the x in parentheses and whatever inside the parentheses.
That's exactly what I do. Sir?
Is there any other way to know the cube root of a number other than just knowing the root?
You have to use a calculator, but sometimes I won't give you calculators. I'm going to expect that you know cube roots for like 7s and 8s. I mean, seriously, that's all it is. 49 times 7. I mean, it's got to end in a 3. Okay? Things like that. 243. Or whatever one. But it's got to end in the 3 when you multiply it out. 8. So it'd be 8 times 64. Well, what's 8 times 4? It's got to end in the 2. So it's little things like that. It's just multiplying. Okay? Same deal here. And you've done this also. This is another method called factoring by grouping. And you've done factoring by grouping when we had quadratics that had a leading term coefficient that wasn't equal to 1. Remember how you multiplied your tails together, you split the middle term, wound up with 4 terms. You take GCFs out a couple times. It's the same thing, guys. The only thing is that you're starting with a higher degree polynomial. People always ask, when do you know when you're going to have to do what? Well, if you see 4 terms and there's no GCF and it's a 3rd degree polynomial, you're probably going to be grouping. Okay? So when you're grouping stuff, it's just a matter of getting the GCF out of the first 2 terms and trying to mirror that in the second. So what's going to be your GCF of x cubed minus 2x squared? X squared. So I factor out, I put this in parentheses, I factor out my GCF and I get x squared times x minus 2. On the next group, since that 3rd term winds up being negative, always remind yourself that you have to factor it back out. What's the GCF of 9 and 18? The idea here is that you want the stuff in parentheses to be identical to each other. If they are, you've done good. So you write it down. And what's left? X squared minus 9. Now, am I fully factored? No. What can I do? Yep. I can factor out this further to get x minus 2, x plus 3, x minus 3. What changes if it said equals 0? What are your zeros?
3 and negative.
Yep, 2 plus minus 3. Good. All right. What are your tails doing? Down, up. Okay. Let's try another one. Look at this one first. 81x to the 4th minus 16. So in this one, you've got 2 terms and a subtraction symbol, which means you should probably check, well, is 81x to the 4th a perfect square? Yes. 9x squared. And is 16 a perfect square? Is that a subtraction symbol?
Yes.
So you can treat this exactly like you would a difference of squares. You get 9x squared minus 4 and 9x squared plus 4. Can I go any further? With the first one, good. What does the first one break out to be?
3x plus 4
Thank you. I can't do that on the other side because of why? Because it's a plus. Okay. What if I do this? What are going to be your zeros? Guys, stop talking. It's a no. Pay attention. Okay. Plus minus 2/3.
Plus minus the square root.
Okay. It's the square root of 2/3.
It's plus minus 2/3.
Minus 2/3. Yeah.
Well, if you set this equal to 0, you get negative 4 over 9. Square root it. What's the square root of negative 4 over 9?
Oh.
2i over 3. Plus minus 2/3 I, or 2i over 3. I did. If I had to solve this for 0, add 4 divided by 9, take the square root, I get 2/3, plus minus 2/3. I just factored it further. The difference here is, guys, that if the problem's asking you to factor, you factor it fully. If it says find a 0, sometimes you don't have to factor all the way because you can just get a 0 real quick. Yeah.
We didn't technically have to do that only if it had like the 0.
Yeah.
Okay.
Yeah. I was just seeing,
Yeah,
just
okay.
because a lot of these problems are all the same. It's just a matter if it does it equal 0, does it not equal 0, stuff like that. So I'm just trying to show you a couple of them all. What I do?
So what is it?
I found the zeros. Of what? This one?
The entire thing.
I set it equal to 0 and found the zeros. I factored it.
Okay.
Is this a perfect square?
Yeah.
Is this a perfect square? Is that a subtraction sign? So you're good with this then? Okay. Is this a perfect square? Is this a perfect square? Is that a subtraction sign? So you go with these two then. Can't do anything here, right? Okay. So this is your fully factored answer. I asked after that, find the zeros. Subtract 2 divided by 3. Add 2 divided by 3, that's where I get the plus minus 2/3. On the other one, I'll get you 1 second. On the other one, if you set it equal to 0, you have 9x squared equals negative 4. Divide by 9. Take the square root. Took a square root over an equal, I get my plus or minus. What's the square root of 4? What's the square root of 3? Sorry, the square root of 9. So this is where I'm getting that 2/3. But what's the square root of negative 1? Just Jones.
All right, so I get how to do all of this, but like, why can't we do anything with 9x squared plus 4?
You can't factor that further. Because is this a perfect square?
Yes.
No. Yeah. Yeah.
Is this a perfect square?
Yeah.
Is this a subtraction symbol? Done. Better yet,
Oh, so it has to be subtraction.
yeah. Better yet, what times what's 36? You add together, you get 0.
Oh, you add here?
Nothing beyond.
Nothing.
No.
It just means it's not crossing the x-axis. It's just crossing someplace else. It flips around someplace else. Don't worry about it. You'll see it. It's very easy. Yeah. Very, very easy. Yes, ma'am. Shh. What's that? Negative 6 plus negative 6 is negative 12. Same deal here. Maybe this one is another. Let's just factor this one fully. 4x to the 6th minus 20x to the 4th plus 24x squared. First thing is take out the 4x squared. Good. Factor out a 4x squared. Now I have x to the 4th minus 5x squared plus 6. When you see a trinomial whose degrees are getting cut in half each time down, factor it the exact same way you would a quadratic. What times what is positive 6. You add together, you get negative 5.
Negative 5, negative 3,
Negative 3, negative 2. Notice what I did there. I just dropped it to x squared minus 3, x squared minus 12. Because if I FOIL that out, what's x squared times x squared? x to the fourth, then I get minus 2x squared minus 3x squared plus 6. That's how that works itself out. Now, FOIL it out. You FOIL this out. X to the fourth minus 2x squared minus 3x squared plus 6. This becomes 5x squared. Like I said, treat it the exact same way as you would a regular quadratic. It factors the same way. Now, if I do that, and I ask you to plot it according to tails, let's see if we can figure that out. It's up and up, good. Where are your zeros? Plus minus root 3, plus minus root 2. Now, question about this. As of right now, it's a 6th degree polynomial. You have listed 5 possible zeros. Is there one of them that may be repeated? No, this 2's not a perfect square. Then it'll be x squared minus 1. This, since it's on the outside, that's, remember what we call that? Multiplicity? It has a multiplicity at 0, which means it's repeated at 0.
Wouldn't it be like x squared equals 0?
What happens here, guys, what happens here in order to figure this out is that you're setting each of these terms equal to 0. That's why you guys were to say, oh, it's plus minus root 3. Oh, it's plus minus root 2. Here, I can say this is 4x times x, can't I? Which means I have 2 other parts I can set equal to 0. That's where I get 0, and then I get 0. It has what's called a multiplicity at 0. It's a repeated 0. If you have a repeated 0, that means you change direction at that value on the axis. Okay? So your graph negative root 3, negative root 2, 0, root 2, and root 3. It would have to look something like that, right? Your tails are up because it's a first term positive with an even exponent, which means it's working its way down, changes direction, touches, changes direction, down, and back up. And it'll look exactly like that. Back in 6.2 when we did our dancing moves, changing direction. Alright.
How do we want that if it's just that?
That's the whole idea of the number of zeros that you have. In this case here, we have a 6th degree polynomial that can have up to 6 zeros, one of which is repeated. A repeated 0 an even amount of times means it's just touching the axis at that spot and changing directions. Yep.
Okay, so that doesn't you know, like,
That's how you show that you have that two. That's how you show you have 2 values of 0 at 0.
So is it like, is there like the end of one and start of the other?
What do you mean? Oh, we're changing direction? Yeah, it's a point of inflection. Okay? Yes, sir.
If it was like 4x to the third, would there be like 3 zeros there and it just continues on?
Yeah, but then that works out to be a little bit something different that happens when you have an odd multiplicity.
Okay.
So I'm trying to keep it where it's an even multiplicity because it's a little bit cleaner. You'll worry about the odd multiplicity in pre-calc.
Okay.
All right. What changes now? Mr. Jones, you got a question then?
No, I was just stressing.
Okay.
I wasn't trying to.
What changes here?
Nothing.
Yeah, just gotta move it over to the other side to start out. Solve for 0. Take a minute and go for it. Get your zeros. So let's see here. You get 2x, x squared minus 4, x squared minus 3. 0 is at 0, plus minus 2, and plus minus 3. Okay. Fifth degree polynomial, I have up to 5 possible zeros. Got 0. We did. You got x plus 2, x minus 2, so I just wrote x squared. When I get to a point like this where I'm solving for zeros, I know what my zeros are here. It's plus minus 2. I know my zeros here will be plus minus 3. I'm not showing that step. You don't have to. If you want to go ahead and write out the next step here, you would have x plus 2, x minus 2. This one would, I mean, you can't factor that one any further. So once you get to the zeros, if you just want to add 4, take the square root, it's just plus minus 2. Yeah?
Does every single column have a 0?
No? If you factor out a GCF, there's usually a 0.
So if there's just like a 0.
Remember, you have a separate term. You're setting all of these equal to 0. Set 2x equal to 0. What makes x 0? 0. That's all it is. Okay? Let's do a group one. Three x cubed plus 7x squared minus 12x is 28. Obviously, the first thing you have to worry about is getting side equal to 0, so you have to move. Now, what I would do a lot of times with these types of problems, guys, when I'm reading them in the book and I'm writing them down on paper, I would just move the 28 right away as I'm writing it down. You have to do it anyway. Save the paper. We're environmentalists.
Coming from the guy who says, don't worry about how much paper you use.
It's true. I still might like the environment.
We're environmentalists, but it takes us half of a sheet of paper to do one problem.
Oh, you haven't seen nothing yet. It's GCF the first terms. Let's cut it out. What's that? If you start doing that, you can't, I mean, yeah, you can, but a lot of times you might get in trouble. Put them in a descending order, it'd be a lot. It's just as fast. You might get in trouble with your signs. I've seen people do that and they get lost. Okay. Take out the x squared. Take out the negative 4. And again, once you have something where it's a difference of squares, x squared minus 4, you should be able to do that pretty quick. You get plus minus 2. And what's your other 0? Yeah. Those are your zeros. Yeah.
How did you get the 2 parentheses?
Here?
Yeah. Oh, it's the thing. Okay, never mind.
I did the GCF. Yeah, that's the whole idea. And then I took out, I knew that I'd do a plus minus in here, and I wanted to make this into a 3x, so I had to take out the negative 4. You always try to get those two to match out. It's really the stuff that you're doing here, guys, really hasn't changed a whole lot when it was the quadratic. You just have a higher degree. That's it. Yes, ma'am? Because it's not a squared term. Not always. It really depends on the problem. You can't just fall back into the what's going to happen every time. Remember, all I am doing here is just the same way as it was before with quadratics. You set each term equal to 0 and solve for x. That's all I'm doing. That's all I'm doing. Set each term equal to 0, solve for x. That's your 0. Let me give you guys some problems. Oh, page is closed. I want to say it's 324. Thank you. $349. Yes. 33 to 84 every third, please. Seventeen, right? Well, what's 84 minus 33? Divide that by 3. 17. There was a 7 in it. Let's give her something, right?
Well, no, I was just like, I didn't want to be too distracted.